Hello, today we are going to work on lab 8, actually continuing lab 8. So basically this is the characteristics of the bipolar junction transistor, and basically we did this calculation before and we found all these resistors. So this is the circuit we are going to use. VCC here is 5 volt as standard we usually use, and for R1, for RC, which is collector resistor, we are going to use 1 kilo ohm, which I already have. For our emitter, our calculation said that we have 357 ohm, but since I don't have a single resistor for 357, I will use two resistors in series, 330 and 22. So this number will change a little bit, which is okay, and this is fine. For RG, which is the resistor after the emitter capacitor, it's basically supposed to be 31, but I have 22 and 10, so I will use it at 32, which is fine in series, of course. R base 1 also, it's supposed to be almost 12 kilo ohm, and I have 10 plus 2, so it's 12 kilo ohm. For R base 2, it is basically almost 1 kilo ohm, let's say 6 kilo ohm. I have 6.8 kilo ohm, which is fine. The two capacitors, 1.1, I have 1 microfarad and I have 15 nanofarad. I will start by putting the transistor, the NPN transistor. This is the transistor 2N3904. So I will use it like what we did in the previous lab. So here, if you look at the transistor, the flat surface, this is the emitter from left, base, collector. So emitter, base, collector. So right now, we connected the collector to line 30. I will start by connecting RC first. RC is 1 kilo ohm, and here is 1 kilo ohm. So I will put the resistor here. Always make sure that everything is secure. And I will extend it a little bit here, so actually we can have enough room to put other stuff, because we have a big circuit this time. So this is what we call it RC. So that means the line 14 will be my voltage source line. Let's put R emitter. R emitter actually are two resistors, 330 and 22 ohm. So we end up with 350. So this is, I have the two resistors here for the emitter, and I usually bend the resistor out like this, so it will be easy to install in the circuit. And I will connect it here, alright, and in series that means you have to connect the second one on the same line. So I'll go up here so I can get space. So right now this is the emitter resistor coming from the emitter to this point, which is 40, and then go to line 45. That means this line 45 will be my ground line, which will be defined as this whole line here in the circuit. This is our emitter. Now we can start connecting our base 1. R base 1 coming from the base of the transistor and going up here toward the power supply. So let's connect R base 1. R base 1 actually is a 12 kilo ohm, so two resistor, 12 kilo ohm. And I will go to the right because this is where the collector is. So here, this is the first one. This is R base 1, and this is the second, and I will connect it to the end terminal. So a quick note, be careful when you connect this resistor that the first one is not touching the resistor you have here, which is a collector resistor, otherwise it will be parallel. So right now at the end, because they are connected here to the same point, which is the power source, I am connecting both of them here to line 14. Let's put R base 2, which is the 6.8. So I will come from the base here and try to extend it all the way to the emitter ground. Here is R base. I will connect it from the base all the way to the ground line, which is the last line in the emitter. So this is R base. So I have R base 1, R base 2, RC, RE connected. Now I need to connect the capacitor. C emitter is the 1 microfarad, and this connection means it's parallel with RE. So basically I will come from the emitter point here. So this is my emitter point, and I go somewhere between. Then I need to connect the RG. So RG, what is RG? RG is two resistors actually. So that means actually you can make this as one smaller a little bit. Try to make sure that nothing is touching each other. So this is the emitter capacitor. RG, what is the value for RG? It is 32 ohm. So I have to use two resistors. This is the first one, which is a 22 ohm. I will connect the 22 ohm here and here. So as you see, I go exactly at the same leg because I don't have enough space. So I go to the same leg as the capacitor connected, and now I have this leg, so I will take the second resistor to finish the 32 ohm from this point till the end. It's connect here from this point till this point. Okay, it looks nice, everything looks okay. I don't like the resistors to be bent like this, so let's take it out and let's connect it again. So I'm going here in the same spot like this. Yeah, that's good. We still have the input source with the capacitor C1. Capacitor C1 here, this is actually 15 nano. This is a tiny capacitor, and it is going to the base point again. And since the base is crowded here, I'm trying to look for a point to connect it, but actually I can do this. I can connect it from here. This is the base, which is line 31. So I will take it from the base of the transistor all the way up to this blue line here. So this is the capacitor going from the base going to this point. It's connected all the way with everything. Again, that means this line will be my input source from the function generator in the analog discovery 2. Okay, so now we define this line as the input. We define this line here to be the power source, so I will connect the power source directly here. We define this line to be the ground. So basically this is what I will do. The function generator is red, the ground is black, and the VCC, you can use orange for this or any other color you want. So I will use white for this now, just to define the point. This will be my VCC line, and this is the ground. So the ground line will be here, which is line 45. Then I will have the last one here, which will be the input source, which will be this line here. So let's revise the circuit really fast. This is a transistor, emitter, base, collector. We connected all the resistors in series. Everything is intact here. Everything looks good. If you want to measure the V output, you need to measure the output from the collector as we did. So any point on line 30 will be the V output here. Okay, let's go and study the circuit. Now we are moving to the actual measurement. During building the circuit, I said that W1 or the wave generator is red, and it's actually the yellow color. So let's connect the wave generator. So the first part of this lab is to build the common emitter amplifier, which we already did it, and now we need to do the DC measurement for VR base 2, VRE, VRC, and the Vout DC, and the current in IC. So let's start first by setting up the signals. We didn't set up the signals yet. So the first thing I need to have a wave generator, and for this case we are going to use 1 kilohertz. We can use 1 kilohertz. I don't care about the period, and the amplitude is 1. So this will be enable, and this will be the channel W1. So this is the first thing we do. Then we have to run a power supply, and again I'm using the red one, which is the positive power supply. It's a positive VCC. So this value, if we remember, it was 5, so let's change it to 5 volts. Okay, and here it is, 5 volt, which is the maximum that power supply can actually generate. So now I have the voltmeter, I have the power supply working, I have the wave generator working, and now we can actually go to the voltmeter circuit and we see what will happen. So the voltmeter, as we said last time, it uses the same channel as the oscilloscope. So I will use channel 1 in the scope, and I will connect it with the wires I'm using. Now the channel 1 will measure one of these things. I can use also channel 2 at the same time, which is the blue. So now I have channel 1 and channel 2 ready to measure anything I want. So what I want to measure? I want to measure VR base 2. So if you remember from last time, to measure the voltage across the base resistor or across any resistor, you need to use the 2 terminals. So I will use channel 1 to measure VR base 2. I know which one R base 2. So I will connect one terminal to the base of the transistor, all right, and the second terminal will be connected to the last one here, the resistor. So basically I'm connecting from the base of the transistor to the last terminal of R base 2, which is a 6.8K. To save time, I will measure also the emitter resistor voltage. So the second channel from the 2 terminal will measure the emitter. So I will connect from the emitter, all right, basically to the ground. Now my circuit is supposed to be ready. So I'm ready to do the measurement. So what I will do, I will run the wave gen, I will run the voltage supply, then I will run the voltmeter and expecting to see signal here. So we said that the first channel, channel 1, measures the VR base 2, and that means the VR base 2 is 2.652, which is very close to what we did in the measurement. And the voltage across RE is actually the 546 millivolt. So, okay, so this is the first two measurements. Now, I will take the channels out. You can always stop the voltmeter, stop the power supply for safety. And you take the channels out from here. And I will use channel 1 to measure VRC. I will move the terminal to the collector and the other terminal to line 15, which will measure the voltage across RC. So channel 1 will measure the voltage across RC, and channel 2 will measure V out. Remember V out? V out was basically the voltage at the collector. So I will connect the blue channel to measure the voltage at the collector itself, and then we run the circuit again with generator, supply, and the voltmeter. Channel 1 gave me the value, of course it's negative because I connected in reverse. So this is VRC, it is actually 1.685 volts. The V output, it's actually 3.351 volts. So these are the measurement. The last thing you want to measure here is the current IC. I don't need to do any measurement actually. So in this case, IC is actually VRC divided by RC itself. So that means it is 1.685 divided by RC, which was 1 kilo ohm, and you can do the calculation to find the current, which is approximately 1 milliamps in this. Part B, he wants me to measure the voltage gain, the RI, R output, and he wants me to measure all of this using the network analyzer. To measure using a network analyzer, we have to do some connections first. So it is simple, but we need to do it in detail so we can actually find this measurement. Now I will show the circuit, show you how you can connect the analog discovery tool so you can actually do the measurement for part B. So part B requires you to do AV measurement using the network analyzer, and it wants you to do also R input and R output measurements. So I will start first by explaining the connections you have here in front of you. As you can see, the red wire here, this is actually connected to VCC. So this is basically the positive V coming from the power source and the device. The yellow one here, which connects to the capacitor, this is basically the function generator W1. And I'm connecting channel 1 here. So let's reverse them first. So I will connect channel 1 of the scope to the base of the transistor. So this will be measuring the input, and I'll connect channel 2 to the output. And the black line here is the ground for the whole circuit. So this is all the grounds I have. If you need more ground, you can take wire from one point here and go to another point so you can connect. So this is basically the connection, and you can go and run the board diagram and take the phase and take the magnitude. You don't need the phase, so you only need the magnitude to give you V out over Vn, which is AV. For the second part, to measure R input, let me disconnect here. So I take this out and this out. So the two channels that will measure out, everything else is in place. And now to measure the R input, what I will do is to bring a resistor similar to the input resistor in the problem. So basically it's 2 kilo ohm almost. I will remove the channel from here, connect the 2 kilo ohm here. So I will put it here, and then connect the actual input, which is the yellow line here, which is a function generator, to this point where the resistor is already connected. Connected channel 1 to the same point. So let's move this back here and connect this here in the empty line. Channel 2 connected between the resistor and the capacitor here. And this will allow you to measure the input resistance. And you run the network analyzer, as we'll see. Okay, this is my starting point for this part. This is my circuit, nothing changed. Now what I want to do is to actually measure the output resistance. And to measure the output resistance, I will bring another resistor equal to the R output. That means it's 1 kilo ohm. So I will bring 1 kilo ohm, and I will connect the 1 kilo ohm to the collector, it's the output point, to any point here. That's good. And then I will ground the input of the circuit. So I don't need this one to go here. So I will take the function generator, connect it here to the actual resistance. So this is connected now on the same resistor. And I will take number 1 and I connect it to the same point, channel 1. Channel 2 will be connected to the point between the output, to the end of the resistor basically. but I'm missing one point now. I need to ground the capacitor here, so I will ground the capacitor with another wire. So this wire, sorry, this wire need to be here, and this wire will go connected to the same ground lines as the one I have here. Now I will run the function generator again, and I will measure the output. To work us through part B, we are going to use the network analyzer to find the voltage gain and the input resistor as well as the output resistor. First of all, you need to start having the network. So the connections here, basically you should have channel 1 connected to the input, which is V base, and channel 2, which is the blue, connected to the output defined as the collector, and the negative value is actually going of this channel is going to the ground. So we come here to the screen and we go down here to network. So choose network. All right, this was previous network runs here before. It will actually, it's okay. So I'm adjusting here to the 50 millivolt. I have this in relative to channel 1. I adjusted the frequency here from 10 to almost 25 megahertz, and if you can't find 25 hertz here, if the maximum is 10, just to go back here to the wave generator here and click this small icon here and go down. You can change the frequency from limited frequency, which will stop you at 10 megahertz, work also for this, to 50 to extended, which will give you 25. For the current situation, we don't need to go higher than this. So this will keep it at limited, and that means my maximum frequency will be 10 megahertz. I'm collecting only 100 samples. I can actually increase the samples to 200, but this will only give me more precision and will increase the time that it will take. I don't need channel 1. Basically what I'm looking at channel 2 right now, and I will go here and click single run, and here it is. It starts collecting its data. It's 2 at the beginning because of the sampling rate I'm using. Then it will increase the speed and the finish. And here it is. So this is the lower. So I go to here at almost 1 kilohertz or any part in the flat area in this part, and you can actually measure the point at this value here, and this will give you the actual value for this. For the second part, to do the R input measurement, basically what we need to do to calculate R input, I will need to insert an input resistance. So let me stop this thing, is the power supply here. I will need to insert input resistor with the actual calculated value or close to it. So I will have 2 kilo ohm. I remember we calculated the input resistance, which was given in the calculation part to be 2 kilo ohm. So you connect it after C1 and before the input function generator. So I will connect it between C1 and the function generator. Then I connect C1, connect the function generator again. All right, and now I will connect one plus to the input with the function generator. So both of them will be connected to the same point. Then I will bring channel 2 and connect it between the resistor and the capacitor. So all of these are in the input, and of course the negatives are going to the ground. Then again we are running here at the same, so we are going to use the same network to calculate the input resistor. So what we are going to do is to have the start at 100 hertz. So let's put the start at 100 hertz approximately, and the stop maybe 1 megahertz. So I will keep it at 10 megahertz right now. It will not harm anything, and I don't need channel 1. I will run the boot plot will be given to me, so I will run it. It looks like that the gain is a little bit high at the top. So basically what I need to do is to change this minimum point. So I will change this minimum point to something, let's say 10 or 20. And look at the top one, make it higher a little bit, maybe 50 or 90, right? And I will make the stop at 1 megahertz. So the stop here at 1 megahertz. Then I will change the top again to maybe 10 or 13 to look at actually the value that it's calculated here. So make it 20 for now. All right, so we can stop actually at 200 hertz. And then I will run the actual boot plot again. Okay, and then I will go here and measure at this point and see the actual output. So this shift is different here, so we only need the flat area here. So I will measure this one, should equal Ri, the input resistor, divided by R input I bought here, which is a 2 kilo ohm plus Ri. So this will be the function Ri divided by the sum of R input I gave plus Ri, and you can use it to calculate Ri. So to find the cursor, we go here at view and you see cursors. Now you can go ahead and click on plus normal. So this is the plus one, and then you can click on the delta if you want, but I need only the plus for this one. So this is the plus here. All right, so it gives me the value negative 5 dB. Then the last part is to measure R out, and to measure R output we will do some small changes here. Measuring R output, basically I will switch the things. So instead of doing this in the input, I will disconnect the inputs and go to the other side, so the rest is normal. So now we can actually run the power supply first, don't forget this one, and the function generator will be running automatically depending on these values. And let's see what will happen here for the output resistor. So I can actually extend this to 10 megahertz. Just want to see what's happening after this point and run it again to see what's happening at the end. At the same time, I will expand this a little bit up. So maybe I will start from 0 here to be higher. Let's okay, so we can measure here in this area, and this is almost, the dB here is almost negative 10 or negative 9.99, which is actually the R output. This actually will represent R output divided by 1 kilo ohm plus R output. This will conclude part B. Now let's do the third measurement in part 1, so it's part C. Part C wants me to apply a 5 kilohertz 40 milli. So I'm stopping these things here and look at the wave generator. So this is 40 millivolt and the 5 kilohertz sine wave, and you can look at the sine wave, it looks nice. This is 40 millivolt up and down. Then he wants me to use a time domain waveform using the scope to look at the function. So now I would like to run the power supply. I am connecting the function generator as normal. I removed the resistors I used last time. So I'm connecting the function generator to the input, and I have channel 1 connected to the same point. I have channel 2 connected to the collector, and I have my grounds fixed well. If you don't have good grounds, you will have a lot of noise this time. So let's go here and look at the scope, and this is my scope, and I will look at functions similar to this one. So basically what I'm looking at now is the time domain function. So I'm adjusting this to 100 micro. Actually, I can change it to 200 micro per division. This will give me more. I think, let's have a look at it. Let's keep it at 50 micro for now. Oh, it's too much. I will keep it 100 here, and I have a channel 1, channel 2, adjust it to 20 millivolt and 20 millivolt. All right, and I will run the function, and this is the output I have from my circuit. Now let's go ahead and do the second part of the measurement in part C here. So basically he wants me to measure the total harmonic distortion, and to do this we use a spectrum analyzer. Basically it is the same connection as what we had before, so I will not change anything in the connection. I will have the function generator and the channel 1 of the scope connected to the V input. I will have channel 2 of the scope connected to the V output, while the negative of both the channels connected to the ground of the circuit. Please be sure that the ground is connected very well, because this circuit is delicate. If the ground is not connected, you will not see any signal, and it will be very bad. So let's go here, it's welcome, and let's choose the spectrum analyzer. So I'm running the spectrum analyzer, and this is the spectrum I ran before. And as you see here, we set up, okay, we don't need this for now. We set up this from 0 hertz to 20 kilohertz, which is enough for the signal we have. I'm set up the top. If you don't see the signal is a little bit negative, so the top is negative 20. The bottom is negative 90 volt, and you can see here that I have trace 2 only shown. I don't need trace A. I can have it, but I don't need it. And I will change this number to 10 to get the average. And I make sure that the function generator, as a wave function generator, is running, and the sine signal is already enabled, and the pulse here is running too, and it's mastered enabled. Then I go to the spectrum and I run continuously, and now it looks like the signal is taking the average every 10. I can make the signal cleaner if I take this, for example, every 20 count. So this is actually, I change this one from sample to line dB average, and I wait a little bit until it's actually ready. So this is the frequency we have here, and I have the count over 20 to get a larger and neater signal. And actually now we can go ahead, go to view. So open view, so click on measurements, then I'll click add, and here I don't have trace 1, so I need trace 2, and on trace 2 I will choose dynamic measurement. And if you click the arrow here, you got all these different measurements we have, but basically this time we are measuring the THD, the harmonics here. We need the total harmonic distortion, and click on this one and click add. The values we need, all what I need is this value only, so I can actually, I don't need the frequency, I don't need it, but actually let me show you what's here. It didn't measure the frequency actually, but it measures this value of the harmonics here. So this is the total harmonic distortion in dBc, as you see, and actually you can convert it with a simple formula, which is actually 10 to power this number divided by 20, and then multiply this by 100 to get the percentage for the total harmonic distortion. And this will end part C of this measurement. Now let's finish the last part. So the last part says that increase the input amplitude to measure the clipping level. So basically what I need to do is to actually have the scope connected as we did before, and all what I need to do is to measure the clipping level of the circuit. So this is the scope running here in front of you. It's connected the same way, channel 1 going to the input, channel 2 going to the output, and now I will this was my trigger level, so it can actually control the signal. Actually I can go here and look at the function generator. We started at 40 millivolt to 5 kilohertz. So this is the one here. I need to see what is the output. I don't care what is the input looks like. So basically I need to change this division from 500 to something I can see like 20. So it looks like it is okay. I can actually lower this trigger level a little bit to 10 millivolt, so the signal will be stable. So this is actually here. So this is actually not clipping. So let's go ahead and I will jump from here to, let's say 100 millivolt, and go back here. Of course the signal is increased, so let me raise this thing a little bit, maybe to up 50, or let's put it at something like here. So the signal is stable. I don't see any clipping, so I can go ahead and increase more. So instead of 100 I will go, let's say 400 millivolt. Okay, so the output, now I need to change the division here. So let's go to 100. It looks like the signal is nice, looks okay to me. So let's go ahead and increase again to, let's say 1 volt. I will jump a little bit to see what will happen. So this is 1 volt. Is it clipped? Is it clipped? Let's see. Let's go to 200. Oh no, it's still not. So it's still okay, no clipping. So let's go ahead and increase the input signal again to, let's say 1.5 volts to maybe that's okay, there is no clipping here. So let's go ahead and go to 2 volts. Sorry, I stopped the scope. So 2 volts, still no clipping, signal looks okay. So how about 2.4? So I increase by, oh, there is something here. So let's go back a little bit. So let's go to 2.1 volt. All right, and maybe I can change this division and still see, yeah. So there is no clipping at 2.1. How about 2.2? So this is 2.2, still signal looks good, no clipping. Can we have it at 2.3? 2.3, no, I don't see clipping, still okay. So when it's clipped, it will start getting flat at the top. 2.4, now I start to see clipping. So if I go test 2.35 as an amplitude for this part, no, it started clipped here. So at 2.35 it actually starts. So this is one way to look at it. He wanted to look at like this with the scope. So I think what you add to this, I can just go ahead and say okay, 2.5, and I have clipping already in the signal, in the output signal. So this will end the actual measurement for the first part for the common emitter circuit for lab 8. Thank you.